नहीं है।
एक बार एग्जिट करके फिर से ज्वाइन करने बोलो।
सर उसको बोल दो।
हाँ ये 2 लिंक ज्वाइन किया हुआ।
हाँ सर उसका एक वर्क नहीं करता तो सर एक वॉइस के लिए और एक डिस्क्रिप्शन करने के लिए।
तो कहीं इसी में
अभी परमिशन की जरूरत नहीं पड़ेगी।
हाँ एक बार हो जाता है। मैसेज डन विजिबल। हेलो
आपके व्हाट्सएप से कॉल करके देखिए, मेरे व्हाट्सएप में कुछ प्रॉब्लम आ रहा है इंटरनेट के कारण, उसमें से बात करिए।
हेलो हाँ प्रवीण आवाज नहीं आ रही है आपको। अच्छा हाँ या तो आप एक ही लॉगिन कीजिए, सिंगल लॉगिन। अगर कुछ हाँ कुछ प्रॉब्लम होगा तो हम लोग इन्फॉर्म कर देंगे आपको। एक सिंगल लॉगिन कीजिए।
सर अच्छे रहेंगे। सर अगर नहीं हुआ तो व्हाट्सएप से आवाज़ शेयर कर सकते हैं। ऐसे करके नहीं माइक में व्हाट्सएप
ट्राई करें।
यस
हाँ स्क्रीन आ रहा है
ठीक है
पर साउंड नहीं आ रहा है। आप अपना माइक ऑन है आपका?
ये सर माइक तो ऑन है।
आप लैपटॉप यूज कर रहे हैं कि क्या यूज कर रहे हैं?
लैपटॉप यूज कर रहा हूँ।
अलग से कोई वो है क्या मतलब जो
हेडफोन?
हाँ हेडफोन वो ट्राई कीजिए।
मैंने हेडफोन ओके ठीक है, मैं हेडफोन कनेक्ट करता हूँ पहले।
हाँ हाँ
ठीक
हाँ 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 आवाज़ नहीं आ रही। हाँ
हाँ जी
हाँ
क्रॉस दिख पाया, बस क्लिक
आपके सिस्टम का इशू हो सकता है।
मेरे पास कंप्यूटर है, मैं कंप्यूटर से सेट करने की ट्राई करता हूँ।
कौन से?
मेरे पास भी कंप्यूटर भी है, एक लैपटॉप के अलावा मैं उसमें ट्राई करता हूँ।
हाँ, उसमें ट्राई कीजिए। तो खुद कनेक्ट कीजिए, मैं इधर चालू रखता हूँ, मतलब पीसी चालू है, मैं इसको कट कर वॉइस को।
ठीक है।
दूसरे डिवाइस से ज्वाइन कर रहे हैं।
हाँ।
Hello?
Hello, Praveen. Hi, yeah, now it is coming.
Okay. Okay, so are you able to watch my screen?
No, the screen is blank. Sound is coming, but the screen is blank.
Okay.
Again, reshare your screen again and try to share the whole thing. Exit your screen sharing and then again share the screen.
Okay.
कोई सारा निकल गया है। एक भी जगह नहीं निकाल दी पापा। ओ भाई
Yes, now something is coming. Yeah, now it is visible.
Okay. So can you see the first
Yeah, now it is visible perfectly.
Okay. Okay. Thank you.
So, okay, I am handing over to the our volunteers.
Okay. Thank you,
That's
sir.
mean the screen went up.
प्रवीण क्या हुआ? शेयर करने का ऑप्शन नहीं दिखा रहा है क्या? स्क्रीन शेयर करने का?
स्क्रीन शेयर नहीं है क्या अभी?
नहीं, हम लोग वेट कर रहे हैं कि स्क्रीन शेयर होगा, क्योंकि एक बार हुआ शो, उसके बाद में फिर से वो विजिबल नहीं है अब, तो एक बार फिर से चेक करें।
आप अपना वीडियो ऑफ कर दें और उसके बाद स्क्रीन शेयर करके देखें।
अभी ठीक है?
Yes, now it is visible.
Okay.
Okay.
Sorry.
Shall we hand over to the volunteers?
Yes, please. I'm
प्रवीण, ऑल द बेस्ट।
Thank you.
Proceeding towards the next session. As you know, gravity is one of the four fundamental forces of universe, and a theory suggests that gravitational waves are ripples of intensity of gravity generated by accelerated masses of an orbital binary system that propagates as wave outwards from their sources at a speed of light. To know more about the gravitational waves, we have here Mr. Praveen Kumar sir from University of Santiago de Compostela. Sir is doing research work at University of Santiago de Compostela, Spain on gravitational waves in LIGO, Virgo and Cadra collaboration project. He hails from Sarghat, Himachal Pradesh. He completed his BSc Honours from Lovely Professional University, Punjab in 2015 and MSc in Astronomy and Space Physics from Punjabi University, Patiala in 2017. He also completed a master's degree in theoretical physics from the Aix-Marseille University, France in 2020 and a master's thesis at Center of Astrophysics, University of Portugal. Sir has completed several internship projects and has participated in many workshops and schools. He also received many scholarships, including the prestigious Summer Research Fellowship from Indian Academy of Sciences and received University Academic Honor Award for standing first in order of merit in BSc Honors. I request sir to please let us know more about your work. Please sir.
Thank you very much for this wonderful introduction. Uh, Firstly, I would like to thank Praveen sir for giving me this wonderful opportunity. And this is going to be my first talk, so you can see that I am a little bit nervous also. So please forgive me if I will not be able to speak properly. Hello, am I audible?
Yes, Praveen, continue.
Okay. Okay, so thank you very much. So let's get started. I am going to give an overview of gravitational waves. I'm not going to go bit deep. It will be just an overview of this field so that you can be you can know about this field little bit. Okay, so I would like to start from very starting, like from the history of astronomy. So way back in the time, Greeks and Egyptians were the first earliest civilizations to pioneer this field. We can start from Plato. Please give attention on this timeline 428 347 BC. I'm talking about BC. So Plato was one of the first person who started this field, and he came up with the idea of geocentric universe. So what is geocentric? Geocentric means that Earth is the center of the universe. So according to him, that Earth is the center, and all the celestial bodies like Sun and planets are revolving around our Earth. And Library of Alexandria was the leading institute of research at that time, because the more than hundreds of scholars were working there and translating the scriptures from other civilizations like Indian, Persian, because these civilizations were also very developed at that time. And later on, Ptolemy came. Ptolemy came, and he also strengthened the same idea of geocentric universe, and he told the world that that the Western countries has the accepted the geocentric theory. But later on, Nicholas Copernicus came with the idea of heliocentric universe, which is and this heliocentric theory says that Sun is the center, and the celestial bodies like planets and our Earth, including our Earth, they are orbiting the Sun, but in a circular orbit. Today we know that these bodies are orbiting in a elliptical orbit, but at that time it was thought that it was thought that it's orbiting in circular orbit. Now later on, Johannes Kepler came with the idea. Actually, he used the data of Tycho Brahe. Tycho Brahe was one of the other researcher who took the observations for 20 years. He was doing it with naked eyes, and Johannes Kepler took the data of Tycho Brahe, and he proved that these orbits are not the circular, they are elliptical orbits. And then we know that Galileo started doing astronomy with the telescope. So you can say that Galileo is the person who we can call him the father of modern astronomy, because before that we were doing astronomy with the naked eyes. And then Isaac Newton came, and he gave us the laws that we know today, that gravitational force, we can calculate the gravitational force between two bodies. So before that we were just observing the things, but now we started calculating after Newton's law. And later, but until Newton's, we were considering gravity just as a force. We were just seeing it as a type of force like other three other fundamental forces. But then later on, Albert Einstein came and he changed our perspective that we can see it as a form of wave also. So we today we define that space tells matter how to move and matter tells space how to curve. Okay, so moving towards next slide. I will talk about electromagnetic spectrum in this. So we know that optical astronomy comes in the visible. It's a visible part of the spectrum. But in addition to visible range, there are other wavelengths also, like radio wavelength, microwave, infrared, ultraviolet, X-ray, and gamma rays. So optical astronomy was the first branch of the astronomy. But then later on, people started doing radio astronomy, microwave, ultraviolet, and all other branches, and we came up with new information about the universe. Okay, so this slide is showing, if you see carefully, the first image, the top one image. This image is of sun, and all the images are of sun. But information about the sun in each wavelength. For example, if we see the sun in X-rays, we came to know about the violent phenomena in the sun. So similarly, each characteristic, each wavelength has its own characteristic and some set of information we get about each object in the universe. So the below image is the image of Milky Way in the different wavelength. So it's the same as the comparison of the sun in the different wavelengths, and the bottom image is the same in different wavelengths of Milky Way. Okay, so let's jump on gravitational wave now. So far, nearly all our knowledge of the universe comes from electromagnetic radiation. So if observing new wavelength of light lead to such revolution in astronomy, what might we expect when we observe entirely new spectrum? So similarly, like we have a spectrum for electromagnetic waves, similarly we have spectrum for gravitational wave too. So we can imagine that we can have more information about the universe and more discoveries in the gravitational wave era. Gravitational waves radiation offers a complementary image of the universe, listening rather than looking. In the next coming slides, I will show that we focus on listening rather than looking in gravitational waves. We can listen the gravitational waves. Okay, so this is a short comparison between electromagnetic and gravitational waves. This slide will change your perspective, like how you should look at gravitational waves and how you should not look at gravitational waves. Okay, so electromagnetic waves are produced by accelerated charges, whereas gravitational waves are produced by accelerated masses. Any accelerated mass can produce gravitational waves. Even we also produce gravitational waves, but the amplitude of gravitational waves that we produce is way smaller than we observe in the observatories for the gravitational waves that we detect in the observatories from black holes. You can imagine, like, black holes have masses like 10 times the solar mass, so we detect that gravitational wave. Okay, so electromagnetic waves propagate through space-time, whereas gravitational waves are oscillations of space-time itself. Okay, so next point is about the frequency. So this point shows the frequency range in both the spectrum. So in electromagnetic waves, the range of spectrum is between 10 raised to power 10 to 10 raised to power 20 hertz, whereas in gravitational waves, it's between 10 raised to power minus 16 to 10 raised to power 4 hertz. And so it shows that they are more like sound waves. Okay, so this is a small video to give you an overview that how the two black holes collide and when they produce gravitational wave and how these gravitational waves propagate in the space. Are you able to watch this video?
Yes, sir.
Okay, thank you. Okay, so you can see here that these are the binary black holes and they are spiraling each other, and at the end they got merged and they produced gravitational waves. Okay, so in the next slide, okay, so this is the next slide, and it is about the LIGO observatory, that how is the LIGO demonstration of LIGO observatory, that how it detects gravitational waves. Okay. This is a simple demonstration of LIGO observatory, that how it detects gravitational waves. This is a rough scheme of it. I will explain in the later slides more little bit in detail, but this is just an overview. So I want that you should have this thing in your mind, that how it works. These are these are the interferometers. These arms, long arms, are called interferometers. And here we detect the gravitational waves. Here is the screen here. Okay, so next one is the sound of two colliding black holes. How they sound. So this video will tell you the sound. And these sounds are detected by these observatories. Okay, so let's talk about the first event that was detected by this LIGO observatory, GW150914. This was the first event that was detected in 2016, and in 2016, world came to know about gravitational wave for the first time. Even I heard gravitational wave for the first time in my life, that people have discovered gravitational waves, and it's like this. Okay, so GW means here gravitational wave, and 150914, it means the first two letters correspond to the year, and 09 correspond for the month, and the last one is the date. So that means this event got detected in 2015, in the September 14th. Okay, so here I want you to focus on the right hand side picture. If you see these two balls, these are black holes, and they are spiraling each other and falling towards each other, and in the next to it, they are coming closer to each other, and in the next part they got merged, and in the final part, I mean, they got merged and become one black hole. This black hole is the summation of mass of these two black holes, and this red lines is showing the wave that we are getting in the different phase of this black hole. So during the merger, we get gravitational waves. So we get gravitational waves only during the merger here. This is the gravitational wave, and after the ring down, there is no wave here. So this is the wave that got produced here and got produced during the merger, and we detect these waves in our observatories on Earth here. Okay, so left hand side in the bottom image, you can see there are two LIGO observatories. One is in Hanford and one is in Livingstone. Both of these observatories are in USA, United States of America, and these two graphs are showing the comparison of the signal that we get in both the observatories. And it looked like this. I showed you in the sound of gravitational wave in the last slide that it looked like this. Okay, so this box is showing the parameters of this first event. So like I said, it's always a binary black holes. So one mass of one of the black hole was 29 solar mass, and other one had the mass 36 solar mass. And after the merger, it became a single black hole with a solar mass of 62. Now you can ask that these two these two combine each other, but their masses should be 65 solar mass. But during the merger phase, gravitational wave be, got produced, and the rest of the mass, I mean, it went transferred in the form of gravitational waves. So at the end, we got this 62 solar mass, and this event happened at the distance of 1.3 billion light year. Okay, so we detected new events, we always detect black holes. So what is the physics that we can conclude from these type of events? Okay, so we concluded that stellar binary black holes do exist. They exist in the form of binary pairs. They merge within the lifetime of the universe. And the most uh, important conclusion here is that the black holes who have mass greater than 65 solar mass, they cannot be, I mean, they cannot be formed in the form of supernova, formed from the supernova, like as a death stage of a star. So the point is how they got formed. So one theory says that they got formed. You can see this picture, that there are two smaller black holes. So after the merger, they became big one. So this is possible. This is possible that the black holes who have masses greater than 65 solar mass get formed like this way. Okay, so next point is what type of sources LIGO can detect. Okay, so LIGO can detect objects which are in the last stage of in spiral of binary neutron star, merger of stellar and supermassive black holes, or collapsed supernova and pulsars. So right hand side image is showing that when two black holes are spiraling each other, so when they got merged, how the gravitational wave is produced and how the phenomena look like. You say is an animation. And the left image is showing the Lego construction. It's a like a Lego template. Okay, so we have observatory, we detected it, but we got signal in the observatory. But what is the next point? How we detect? What is the ultimate thing after that? So here comes the part of data analysis. So I am doing my PhD in data analysis. Like we have data from the different observatories, LIGO and Virgo, and then we get a lot of data. And so how we perform computing, how we perform, we have many codes. So we do data analysis, statistical, I mean, techniques, and then we detect events at the end. So here comes the part of data analysis. It is a very complex thing to explain, but I will tell you in a I mean simple way that what we do. So okay, so let's suppose we have one detector, or we have n number of detectors. So the first thing is when we have data, so we check the data in a first glance, and we see that which data is very noisy, and there may be some time duration in between which do not have any event, or it do not have any signal. So we what we do, we take out that data. So it's called getting bit to window, that we take out that particular chunk of data which is very noisy or which do not have any events. So after that we do match filtering. So okay, what is match filtering? So we know from general theory of relativity, we know that what type of signals gravitational waves are. So we know it already. So we create fake data similar to the data that we receive through these observatories, and then we try to match the fake data with the original data, and we see that which data is matching and which is not. So the data which is not matching, we subtract that data. So we just have only that data which is matching with the fake data. Okay, so the data we now have at the end is not the ultimate data. It's not like it's like we can use it directly. So that data has to go through a lot of statistical tests like chi-square test, ranking statistics, because we cannot confirm. Let's suppose we have a data and we confirm that there are 100 signal in that, but there can be a false alarm rate, and there may be some noise in that, that is leading to a signal. So we perform a lot of tests in order to get sure that we are not having any fake signal. So at the end we we get the signal. So it has to go through a lot of processes, statistical processes, and it's not very easy to handle data like like in the observational run per day. The LIGO observatory is getting data in petabytes. So every day we have petabytes of data. So you have to handle them. We need very strong computers, systems to handle such type of data. Okay, so this is showing a global network of detectors. So here you can see these these two observatories. These both are LIGO observatories. They are situated in United States of America. One is Virgo. It's in Italy, in Europe. Geo is also in Europe, and one is in Kagra. It's in Japan, and until now, there has been three observational run. One was in 2015, and second one was in 2017, and the third one was in 2019. And these three observatories, two LIGOs and Virgo, participated in those three previous gravitational wave runs. But in the in the fourth observational run, Kagra is going to join, and this observational run is going to start in the next year in March 2023, and Kagra is going to join as a fourth observatory with these three observatories. And this project, LIGO India project, is under construction. They claim that they will complete this project up to 2026. That means that LIGO India observatory will be ready by 2026, and it will after that it will be able to join the observational runs. Okay, so I'm going to tell about little bit in more brief about these observatories, LIGO, Virgo, LIGO India, and Kagra. So let's start from LIGO. So these are two observatories, as I said. One is in Hanford and one is in Livingston, and these are operated by these two institutes, MIT and Caltech, and they are 3,000 kilometers apart from each other. LIGO uses two detectors far apart because its detectors are so sensitive that they can feel the tiniest vibration on Earth from sources nearby to megaparsec. For example, earthquakes and acoustic noise like truck driving on nearby roads, farmers plowing fields, and etc. Now imagine, uh, now I tell you that how much is the amplitude of gravitational wave. So the amplitude of gravitational wave is 10 raised to power minus 21. Now imagine we are observing a wave which has amplitude 10 raised to power minus 21. So you can imagine that how much sensitive we need to make these observatories so that it can detect this much amplitude wave. So these facilities are far apart, but they do not feel the same local vibrations, but they feel the same gravitational wave vibration. Okay, so next point is what limits LIGO sensitivity, or in other words, we can say that what are the possible noise sources. So yeah, so this figure is giving you different type of noise sources that mask the gravitational waves, like suspension thermal, radiation pressure, gravity gradient, straight light, and many other noise sources. So we have to compete these sources in order to finally detect the gravitational wave signal. Okay, so next one is a Virgo observatory, and it's in Italy. In There's a city called Pisa. It's nearby to that, and this is a rough scheme of the rough scheme of Virgo observatory. These arms are of 3 kilometers long. Both arms are 3 kilometers long. In case of Virgo, they were 4 kilometer long arms, and this is the site of Virgo observatory. And this is a comparison of the first signal that first gravitational uh, first gravitational wave that was detected, and is a comparison of that. I already have made this comparison in the previous slides, Hanford and Livingston, and this is in comparison with Virgo. So all these three observatories have this comparison of the first signal that was detected. Okay, so let's talk about our next detector. This detector is going to join in the next observational run. Like I said, it's going to start in March, next year March, and this is located in Jifu Prefecture, and it is at the altitude of 141 meter from the sea level. Its arms are again 3 kilometer long, like Virgo, and it's an underground observatory. The reason why it was made underground, because in order to reduce seismic noise, like I said, they are 3 kilometer long, and this arm is kept in vacuum, and so you can imagine that if you have some vacuum leakage, you can have a noise in the signal there. So you have to keep it like at either level, and it is claimed that it will gain sensitivity up to 10 megaparsec, which LIGO is not able to gain it. So this one is a new detector, very sensitive detector as compared to LIGO and Virgo. Okay, so now talk about LIGO India project. This is a joint project between USA and India, and these four institutes, DC, SEM, RRCAT, IPR, and IUCA, these four institutes are mainly participating in this project. DC, SEM, and IUCA are both situated in Maharashtra, and this site is also in Maharashtra. The IPR is in Gujarat, and RRCAT is in Madhya Pradesh. So you can have an idea that this LIGO project is also like the LIGO USA observatory, that is 4 kilometer long arm. So these four institutes have their they have divided their work, like DCSEM is working on these points, RRCAT have their own goals, and they have divided their own work, and they are working together on this project, and they are claiming that by 2026 it will be completed. Okay, so let's talk about now spectrum of gravitational waves. Like I said, electromagnetic waves have spectrum. Similarly, gravitational waves also have spectrum. So nowadays we have ground-based observatories like LIGO and Virgo, Kagra, LIGO India. So these are detecting gravitational waves who are lying in this frequency range, but there are gravitational waves who lie in this frequency range. So we are not going to explore them now, but in the futures, we people are having ideas that they are building gravitational wave observatories which can detect gravitational waves who have frequency in this range also. So for the moment we are only working in this range. So gravitational waves is in very initial stage. Okay, so these are the other projects related to gravitational waves observatories. So first one is Einstein telescope. Okay, so here this is a scheme of this observatory, and this telescope it will have 10-kilometer long arm. It will have three arms. It's in a triangular shape, and each arm will be 10-kilometer long. Now imagine that LIGO had the arm of 4 kilometer, and this Einstein telescope have 10 kilometer. That means it is like 2.5 times much longer than that. So you can imagine that it can it can detect those black holes also, or it can detect those gravitational waves also which cannot be detected by LIGO, because LIGO has a limitation. It cannot go beyond certain sensitivity, but Einstein telescope can gain that sensitivity. And like it's a very giant project, so 15 or 20 countries of Europe are working on this project, and these are the possible countries, is all are mainly European countries. They are working on this project, and the site is also figured out. It's in Sardinia in Italy. Sardinia is an island in Italy, and they are thinking that in Sardinia they will make and they will manufacture this build this observatory. I think I missed one in between. Okay, okay. So it's okay. So next one is Lisa. This is a space-based observatory, and uh, you can see that it's also in the in the same shape as triangular shape as the Einstein telescope, but its arm will be 5 million kilometer. So it's going to be a very giant project, and they are claiming that they will start this project like up, it will be completed by 2036. So it's a very huge project. People are working on it from last 10 years. So you can imagine, like, I mean, how big project it is. And like more than 100, not even 100, like approximately 1,000 people are working on this project. Okay, so they are fellows program related to gravitational waves. These are to these are the two people who are you can say these are the coordinators, Shaila Dyer and the Brian O'Reilly. You can write email to them and ask them that, okay, we want to do a project there, we want to visit LIGO and we want to do project, and they ask you for to stay there for 3 months, and they provide little bit help also, like in the living and little bit house sharing, and like travel to the observatory. So these type of programs do exist. And like I said, there are a lot of observatories which are under in the building phase, and like LISA gravitational Einstein telescope, similarly LIGO India. So they are like 5, 10, 5, 6 observatories which are under process, and people are working on them. And in some cases, they just have the idea, they have not started the work. So that means they need like a lot of manpower in the future. And after that, they build the observatories. What after that? There will be data. Like I said, in LIGO, every day they we receive data like in petabytes every day. So, and one gravitational wave, like if you say that, if I talk about the third observational run, it was for like 10 months. So it started in 2019, and it lasted up to 2020, up to the COVID era. So it lasts up to 10 months. So that means it the observatory was operational for approximately 300 days. And every day you get data in petabytes, so you have lot of data. We receive so much data, so they need huge manpower in order to analyze that data, and in order to make the observatories in shape, the all the machinery engineering, they need lot of data in instrumentation also. So gravitational wave field is in a very early phase of its I mean, it's life. But yeah, so the future is very bright in this field, and in the future time, you will have lot of PhD opportunities, postdoc positions, even the faculty positions. So I assume that many people will participate and they will come in this field. And this one is the just summary of the what I spoke now. Thank you. So if you have any question, you can ask now.
Thank you so much, sir. Thank you, thank you so much, sir, for your words and making us familiar with the gravitational waves and the way of observing it. I hope it will inspire the upcoming physicists. And
Yes, yes, because like I said, that there are a lot of opportunities in India also, and in the abroad also, because so many observatories are going to build in the future. And so I mean, huge amount of manpower is needed in order to build observatories, in order to, I mean, they need engineering people, adaptive optics people. And after that, once they are built, when they start taking data, lot of people are needed to analyze the data. Like I'm working in data field, I'm doing data analysis, I'm not doing instrumentation. So I get data from LIGO and Virgo, and I do analysis of that data. So now in the fourth observational run, Kagara will also join, so they will have more data this year, I mean in the next observational run. So when the new telescope will come, there will be of more data, so they will need more human power for this. So nowadays, many PhD positions are coming in many universities in India also and in abroad also. So you can apply if there are some MSc students who are thinking that what field we can do or which field you can find positions easily in the future. So I can assure you, like next 10-20 years, this field is going to boom a lot. There are a lot of opportunities.
Thank you, sir. We have a question here, sir.
Okay.
सर माय क्वेश्चन है सर हिंदी में बोल सकते
हाँ जी, हाँ जी, बोलो.
हैं सर ग्रेविटेशनल वेव्स का भी कोई फंडामेंटल पार्टिकल है क्या?
We claim that it is gravitons, but it's not proved. It's not proved like in a laboratory until now. But we claim that it's called graviton, like particle physicists claim that it's called graviton, and they know its properties also, like its spin and other properties. I cannot claim, I cannot say much about it because I'm not a practical physicist. I'm working mainly in data analysis part, but I know that I have studied this thing that it's called graviton, but it's not proved in the laboratory until now. But maybe it like I said, like LIGO observatory has a limitation. It have like a certain sensitivity. It cannot go beyond that. But in the future, there are heavy telescopes, bigger telescopes are bigger observatories are coming. Maybe they will be able to prove it because they will have more sensitivity.
क्वेश्चन और है सर एक क्वेश्चन और है
हाँ जी, पूछिए.
सर ग्रेविटेशनल वेव्स हम लोग को जो डेटा प्रोवाइड करता है वो और इलेक्ट्रोमैग्नेटिक या लाइट जो डेटा प्रोवाइड करता है वो दोनों में क्या डिफरेंस है यानी कि व्हाई वी आर यूजिंग ग्रेविटेशनल वेव्स
Okay, so um, okay, so let's I tell you like okay, so we know that black holes have like very uh, uh, light cannot escape gravitational light cannot escape black holes. We know this, so we cannot observe electromagnet black holes through electromagnetic spectrum, but we can hear its effect. Gravitational wave tell us information about the system. It tell us that information which electromagnetic waves cannot tell us. So it's a different spectrum than the electromagnetic spectrum. In
थैंक यू सर आई हैव अ
Yes,
क्वेश्चन
like in the electromagnetism also we get different information from different spectrum. Like when we study object in optical, we get different information about the object, but that information is not complete. When we study that object in different spectrum, in different wavelength, like in optical, in addition to optical, when we study that object in UV rays, or in IR, or in gamma, or in radio waves, we get other informations also, in addition to what information we had in visible range. So similarly, when we study that object in gravitational range, we get other information in addition we had earlier from the other, other spectrum.
थैंक यू सर वी हैव अनदर क्वेश्चन
Okay.
व्हाट इज कॉस्मिक माइक्रोवेव बैकग्राउंड
Okay. So cosmic microwave background is, we call it CMB. I will not go in much detail about in this field, but they are called it comes under multi-messenger astronomy. Like we have neutrinos, we have CMB, and similarly we have gravitational waves. So this is a field, like we have telescopes also on Earth that detect these cosmic rays. These cosmic background radiations. So these are the radiations from the Big Bang time, and they are present in the universe, and we have calculated its temperature also. um, I don't know exactly. I think it is like 2.73 Kelvin something. I'm not sure, but yes, it's like this. It's a particle. it's a particle, and it's present in the universe, and from the time of Big Bang. I mean, it's a one of the uh, old, you can say that one of the oldest from the time.
Thank you so much, sir, for giving your valuable time. We really appreciate it, sir.
Thank you. Thank you very much.
Thank you, sir. Thank you, sir.
Thank you. Bye.
Thank you, sir.
Okay, I'm going to, you know.